The PicoScope has three acquisition modes, and these are available in the capture toolbar. So the first mode is the scope mode, which is a standard YT display. The second mode is the persistence mode, which again is a YT display but has a persistence display. And the third mode is the spectrum mode, and this is a frequency against amplitude display. And in this section we're going to be looking at the frequency display. The signal currently being acquired is in fact a sine wave, which is being generated in the internal arbitrary waveform generator, and in fact is a sine wave with a frequency of 100 kHz and an amplitude of 950 millivolts. So we can move now to the spectrum display, and this is an amplitude against frequency display. In fact, the frequencies can be captured up to 350 megahertz. In this particular case, I'm going to leave the display as 1.9 megahertz so we can resolve the 100 kilohertz signal. The fourth icon along is the spectrum options. So here we can set up a number of options for the spectrum display. So the first one is the number of acquisition bins. So this is the number of bins that the data is acquired into, and can be up to 1 million bins, which gives a very high frequency resolution. The second option down is the window functions, which can be selected by the user depending on the particular measurements, whether it's important to have the best frequency resolution or the best amplitude resolution. So for example, I could select the Blackman-Harris filter. The third option down is the display mode. So the default is magnitude in dBs, and in fact the scale factors are available in dBVs or dBs or dBms. Under the display mode then there are two other options. Is the average mode, and this will average the acquisition, so any averaged noise will be removed so we can see a better harmonic resolution. And the final one is peak hold, so this will hold the peak of any signals present being acquired. I'll leave it in the default magnitude display. So now we're ready to go ahead and make some measurements. So we could measure the frequency of the fundamental. So we could do this manually with a cursor initially, so we can manually position the signal onto the fundamental and make a measurement. Indeed, this is the 100 kilohertz input. But this could also be done automatically in the measurements menu, where we can add a measurement, and we can select the source of the measurement, and then there's a whole range of frequency measurements available. So for example, we can measure the frequency of the fundamental, which again is the 100 kilohertz signal, and then any measurements can be deleted from the display. So now we've deleted all the measurements. Similarly, we can do amplitude measurements. Again, they can be done manually or via the automatic measurements. So we have two cursors available here, so I'm going to position one cursor on the fundamental. So I'm just going to move the cursor one onto the peak of the fundamental, and I'll move the second cursor onto the peaks of the harmonics. So here we see the measurements in amplitude. So the fundamental is minus 1.4 dBs, and the harmonics are minus 61 dBs, which gives a delta of 60 dBs. A similar measurement can be done in the automatic measurements. So here again we can select the source as A, and here we could select, for example, signal to noise ratio and apply. So this is measuring the amplitude of the fundamental, but also measuring then the amplitude of all of the harmonics and doing an RMS and doing a dB ratio from the fundamental to all the other components. So here we're seeing a RMS value of 49 dBs. Again, I'll go ahead and remove that measurement. So the final set of measurements we're going to look at are the total harmonic distortion measurements. So again, there are three total harmonic distortion measurements available. There's one as a percentage. The second measurement is available as the dB ratio, and a third total harmonic distortion measurement is total harmonic distortion, but it's adding the addition of the noise floor. So here we see the three measurements. So looking at the percentage measurement, and we see it's a very low figure because it's a very clean signal. And in fact, it's minus 56 dBcs, and in fact by adding the noise the figure is only slightly larger. So to illustrate this a little bit more clearly, I'm going to distort the input signal. So I'm going to select the arbitrary waveform and I'm going to distort using the pencil. I'm just going to flatten the top of one of the peaks and add some distortion to the signal. So I'm going to apply that change. So this will have the effect of increasing the harmonics. So here we see the harmonics have come way up. So in fact the total harmonic distortion in dBs is now minus 26 dBs, which gives the percentage figure of 4.8%, because we can see the harmonics now are way up due to that distortion. So if we look at the YT signal, we can see we've distorted that signal with the flat top.